recording. All right. Everyone, just wanted to, everyone can see this right online? Is it displaying properly? Can you hear me clearly? Cool, okay. Right, I thought we'd just very quickly take a look at this last example. I think I rushed through it last time. And a couple of mentions also is that REGZ submission is due today, the third one by the 11:55 p.m. today, and the midterm exam will be available Thursday 9 a.m. And the final exam is going to be on the 28th of November, on the Monday. So thanks to those that have let me know about if you have issues with that. Continue to let me know if you don't, if you do. And do keep in mind that you should have a UNSW ID and an approved calculator with the UNSW sticker, approved sticker with it. And it will take a bit longer it will take a couple of days to get the IDs. So if you don't have one, make sure you sort that out before the day of the exam, or the final exam. Okay, any queries before we get started? Okay, let's move on then. Up to what, according to, as stated in the course outline, we'll cover the first two topics. So just the topic on exponential and logs and trigonometry functions. Cool. I had a look at it. It's going to be a little bit different, so I sort of didn't want to give you. I was a bit worried if I give you the 2021 that it might not be a complete representation of the final. Is that still the main thing that you'd want to see? Let me think about it. Yeah, just because it's a little bit different, so I don't want to sort of put that up and then it's not what you expected. Yeah. Not very. It's sort of similar difficulty, but not. Yeah. No, it's just the type of questions. It's going to be pretty much the same as last terms for term 2's midterm exam in terms of format. Yeah. So I sort of yeah. Cool. Okay, any other queries, questions? Okay, so let me just have a little pause to see where we're up to. So yeah, so I sort of rushed through this a little bit, so I just want to sort of just sort of run through this for 1 or 2 minutes. And this was just one of the applications of arithmetic series where we had these cans, right? So we noted that the first row has 5 cans, second row has 7, and third row has 9. And with these 3 pieces of information, if we want to calculate the number of cans 11th row down, we're simply asking T11. I did start recording here. Yes, I did. So this is an AP with A's initial term 5 and common difference 2. So simply substituting in the values for n is 11, we would end up with 5 plus n minus 1 is 2, so 2n plus 3. When n is 11, that would give us 25. So there's 25 cans in the 11th row. And the second part was if we have 320 cans altogether, so that's the sum of all the rows, we want to work out how many rows there are. And the idea with this one was we have Sn, we're given Sn, we know A and D, but we wish to solve backwards for n. So given Sn is 320, A is 5, and the difference is 2, this would give us a quadratic equation. So rearranging the terms a little bit, we'll end up with n times n plus 4 is 320, and we would follow the steps to solve for n. So we'd effectively get n squared plus 4n minus 320. this ends up having roots 20 and minus 20 and 16. And 16 is the only one that makes sense for positive number of rows. Okay, so there's 16 rows in total. So I just wanted to make sure we covered that one. Okay, so moving on to today's stuff. Any queries about that last one, last example? Geometric sequences. So what is this all about? So similar to arithmetic sequences, which had a common difference, we say that a sequence is geometric, is a GP, if the ratio between successive terms is a common constant. So we would say that t on t n minus 1 is some constant r, where this is the common ratio as opposed to the common difference. And so these things are called geometric sequences. They decrease geometrically. And the idea really is that to get from one term to the next, we just simply multiply by this value of n. So each term is r. So each term is r times the previous value. Of course, some standard examples is we multiply by 2, so 1, 2, 4, 8, 16. What about this sequence? What is the common ratio here for 1, 2/3, 4 9s, 8 27s? Any thoughts of the common ratio there? So Peter says times 2/3. Do you agree with that? That r should be 2/3 in this case. Yeah, 2/3 times 2/3 is 4 9s. Multiplied by 2/3 is 8 on 2 7s. So that is also a common, is a GP. What about this one? Is there a common ratio here? -1 on 2. Yeah, exactly. So just to spell that out, here r is 2, here r is 2/3, here r is -1 on 2. So it can be a negative value as well. And very similar to arithmetic sequences, geometric sequences are really just points that lie on an exponential curve. So something that follows the power law. So if we think about something like Tn, well, if let's say we doubled it, we would have one at 1, 1, we'd have one at 2, 2, 2, the next one would go through 2, 4, and the next one would be 2, 8. So these are all expanding exponentially in a sense. So here's an example of one that's not quite 2, but a slightly different number, greater than 1. And you can see these all lie on an exponentially increasing curve. Whereas if the ratio is less than 1, then we'd expect that we're decreasing. So say something such as halving the terms. And this would be exponentially decreasing or decaying. So this would be referred to if r is greater than 1, this would refer to if r is less than 1. What do you think happens if r is equal to 1? It would be a straight line, yeah, if we don't multiply by anything. Well, just 1. Exactly. So if we want to show this as a geometric sequence, what would we do? How do we show this as a GP? Any thoughts? Why would this be a GP, a geometric sequence? Well, not quite the difference. We wouldn't pick the difference. Sorry. Check the ratios. Do we agree with that? Common ratio. Exactly. So if we look at these values, we're just halving each time. So 40 divided by 2 is 20. Divided by 2 again is 10. So we're just multiplying by 5. So just check each ratio. T2 on T1 is 20 on 40, 1/2. T3 on T2 is still 1/2. And T4 and T3 is still 1/2. And so, and we would expect we would just continue by halving each term by multiplying by 1 on 2. So it's a GP, it's a geometric sequence with the common ratio 1/2. What about this one? So, so it's a half, 1/3, 1/4, 1/5. Why? How is this not a GP? Why is this not a geometric sequence? How can we show that? Any thoughts on how to test for this? I guess all we have to do is just check that it's not a, yeah, Iman's got the common ratio. Thanks. We'll touch on the formula in a second. So I guess we will just check each common ratio and see that that's not equal, right? So if we check T1 on T2 on T1, it's a third on a half, which is really 2 on 3. If we divide by this fraction, we would multiply by the reciprocal. So it's really a third times 2. And even just taking the next one over, this becomes 3 on 4, a quarter on a third. And these are not equal terms, so immediately these don't multiply by the same ratio, so it's not a GP. And these, as Iman has alluded to, this actually gives us a, yeah, we're multiplying by 0.5. Yeah, exactly. If we look at a general term for the nth term of a GP, well, it's very similar to the nth term of an AP. So in this case, we would have that our general formula is A times R to the n minus 1. So compare that with the AP term, and you might like to convince yourself why that holds. So you can use a very similar argument, except that these points lie on a curve, not on a straight line. Okay, so it has form A times R to the n minus 1. And if we want to use this, well, first let's check that this is a GP and find a general formula for Tn. So 1/9, 1/3, 1 and 3. Does it have a common ratio? What do we think? 3, do we agree with that? It has a common ratio of 3. One ninth times 3 is 1/3. 1/3 times 3 is 3. 1 times 3 is 3. So yes, it has a common ratio. By checking its consecutive term, you can write the explicit fractions as previously. So it's a GP with R as 3, and the first term is a ninth. So the general nth term will be a ninth times 3 to the n minus 1. So the nth term is given by this formula, which is this. And we can simplify this a little bit because I'm noting that 9 is 3 squared. So you can also write as 3 on n minus 1 on 3 squared, which is a nice simple form of 3 on n minus 3 if we use our power laws. And just as a check, if n is 1, we'd get 3 to the minus 2, which is a ninth. If n is 2, we'd get 3 to the minus 1, which is a third. So you can check that actually makes sense with this sequence. Okay. What about this one? So find the 10th term and 15th term of the sequence. Any thoughts? How do we find this one? Well, probably the first thing is, yep, it's a common ratio with a minus a half. Excellent. So it has a common ratio of R equals 1/2. And where do we go from there?
A is 8.
Yeah, A is 8. That's the initial term. And so that's enough to fix the entire sequence as a GP. And so really, well, we could just find what the general nth term is, and well, that's going to tell us what the 10th and 15th term is. So let's use those ideas. It's a geometric sequence. A is 8 and R is a minus a half. So we're given the general nth formula, form A times R to the n minus 1, which in this case is 8 times minus a half to the n minus 1. So be careful, this minus should be inside the square, inside the bracket, because it alternates sign here. And you could potentially simplify this a little bit, but I think in this case, it's probably just easier to substitute the values in because we're just up the 10th and 15th term. I believe you could also note that this would also be 2/3, so you could also write it as 1/2 to the 3 plus 1 minus 2. So I think that should be 2 minus n, but again, it's probably just simpler to use this straight away. minus 1 to the n minus 1. So that would be important to keep that in brackets at minus 1. In any case, to find the 10th and 15th term, simply substitute in n is 10 for the 10th term, so it's 8 times minus 1 to the 10 minus 1. That's going to be a minus overall because it's an odd power, and 1 on 2 to the 9, and then times by 8. So it'll end up being something minus 1 on 2 to the 6, which is 64. But really, you can just compute it at this stage. Same for the 15th term, it's going to be this expression. Anyone have a guess of what that's going to give us? So what do we expect the 15th term to be? T10 is minus 1 on 64. What's T15 going to be? Eight times minus a half, all to the 15 minus 1.
1 on 2048.
Rory says 1 on 2048. Is that what other people get? Agreed. What do we get for T15 in chat? Sorry? Pretty sure it's, yeah, 2048. So it's going to be a plus because it's 1 on 2 to the 14, and so times by 3 is 1 on 2 to 11, 2 to the power of 11, which is going to be 1 on 2 on 2048. We know all our powers of 2 off by heart. But yeah, so those are the terms. Let's check this one. So find the first 3 terms of a GP, in which the 6th term is 160 and the 7th term is 320. Well, can we work out what the first 3 terms would be? If we're given that T6 is 160 and T7 is 320. Is it pretty obvious what the ratio is, by the way? Yeah, so I mean, in this case, it's just 2 consecutive ones, so it's going to be 2. To see this a more general approach, we could substitute the values. So T6 is 160, T7 is 320. Using the GP formula, T is A times R to the n minus 1. So 160 is A to the R to the 5. So remember that's 6 minus 1. 320 is A to the R to the 6. So that's 7 minus 1 there. Should have noted that there. And so simply dividing 2 by 1 would give us R itself. So that's going to give us R as 2. I mean, of course, you could see that between consecutive terms, but if this was, say, maybe the 14th term and the 19th term or something, this would be a bit of an easier way to do it. So the common ratio is 2. And, well, we can just use the fact that we know that the, say, the 6th term is fixed at 160. By the way, is everyone happy with this slide? Just to check, we're okay with that move. Using simultaneous equations to solve for A and R, just the powers this time. So instead of subtracting, we can divide by this to get the common ratio. Okay, so if we believe that 320 on 160 is 2, that's the ratio, then using the fact that we know that A to the R to the 5 is 160, but if R is 2, then we'll end up with 160's A times 2 to the 5, and now it's a matter of solving back to find A. So that's 160 is 32A, divided through by the common 32 would give us 5. So the initial term is 5, and that's enough to give us the GP, because the initial term is 5, and R is in the common ratio is 2. So the first term is 5, second term is twice that, multiplied by 2 is 10. And what do we think the third term is? Sorry? 20, yeah. So multiplied by 2 again will give us 20. Okay, comments on this one, this example? Okay, so like if we're happy with these sorts of questions, Same with APs, is that we can actually find a general sum for solving a geometric series. The sum of the sequence, which is a series. And the idea is if we have a common initial term A and a common ratio R, which is not 1, then we can express it in either of these two formulas. So we can express it as A times R to the n minus 1, or divided by R minus 1, or equivalently, it's A times 1 minus R to the n over 1 minus R. They're both exactly the same expression. If you think about multiplying by 1 on the top and bottom, minus 1. Except the first one's usually more useful if R is greater than 1, and the second term is more useful if R is less than 1. Basically, just to not have to deal with negatives too much. Right. And I think there's a bit of a proof in the notes to see how we obtain this. So we use sort of a similar idea to the APs, but not the same thing. So as a proof, what are we going to do? Well, let's note what Sn is. It's simply T1 plus T2 up to Tn. We aim for a equivalent formula, closed formula. Well, we can usually use the fact we know that the terms the terms of a GP, so they have this form that T1 would be A, T2 is A to the R, A times R, T3 is A times R squared, etc., up until T times R to the n minus 1, which I can rewrite a little bit. Well, again, yeah, let's just leave it like that. Now, here's the idea. To sort of deal with the sums in between, we multiply by R. So that would tell us that R times Sn is A times R from this first term. A times R is A squared for the second term. A times R squared times R is A R cubed. And you can see that we're going to get the same pattern to A to the Rn. And what do you notice about all these terms here versus all the terms up to here until the last one, which will be plus A to the R minus 1? What do you notice between those expressions? So Sn is A plus AR squared all the way up to AR to the n minus 1. R times Sn is AR plus AR squared all the way up to AR to the n minus 1 plus AR n again. What do we notice about just the underlined parts? They're exactly the same. Yeah, they're the same term. So if I subtract these, if I go Rsn minus Sn, we're going to cancel out all the middle terms. So that helps us get a closed formula, because now I know that this expression left is A times R to the n minus A, and to get S on its own, we can simply factorize the left-hand side. That's going to n factorize the right-hand side. So that's going to give us some term times Sn equals A times Rn minus 1. And what do we do to get Sn on its own? Divided by, sorry? R minus 1. Do we agree with that? We just divide by R minus 1? Yeah. Yeah, so we just divide by what's next to this thing, which I can do as long as R is not 1. So assuming that that's not 1 itself, then we get this formula. Would you know what to do if R was 1? How would you find the sum of the n terms? Any curiosity? It would be, sorry? Well, it would be, yeah, it's an AP with a common difference 0. So it would be the same constant term. Exactly. So if R was 1, you could just sum up, you could just take the sum of A n times. So it would simply be n times A. So there's not really much point in even having a formula because it's just the multiple. Okay, so some applications. Let's say you want to sum the doubling numbers. So 1, 2, 4, 8, 16. How do we get some of the first 10 terms? Well, I guess we have our n right here. Our n would be 10. Our A would be 1. What's our common ratio? 2. So we just simply use that formula, noting that 2 is greater than 1, so the first one's more applicable. So since A is 1, R is 2, N is 10, by the sum formula, we can express Sn as this term and simply substitute the values in. So S10 would be 1 times 2 to the 10 minus 1 all over 2 to the 1, 2 minus 1. And that simplifies as 124 minus 1 because that's 2 to the 10. The bottom is simply 1. So that gives us 123 at the end of the day. So sort of a funny pattern that this actually ends up being 1 less than a power of 2. Okay, happy with this one. Let's try one more. Feel free to say in chat if there's a question. Next one is a similar one. So what do you think for this case? What's our A, what's our N, and what's our R? What are our 3 terms this time? Any thoughts on, well, what's A to start off with? Half. A is a half. Now R, negative half. It's the same example as last time, isn't it? Yeah, so R is negative a half, and we're summing the first 5 terms, so N is going to be 5. So A is a half, R is minus a half, N is 5. The easiest to use the second version because R is less than 1, plus 1 in this case. So using this here, A is a half, substituting in R is 1 minus 1 half to the 5, so be careful that this negative is inside the brackets that we're taking power of, all over 1 minus a half, and now this is going to be an odd power, so it's negative overall inside this component, this term. So we're going to end up with 1 plus 1 on 32 for this term. The bottom becomes 1 plus a half, which is 3 on 2. And if we simplify, well, we will be timesing by 2 on 3. So divided by a fraction is timesing by the reciprocal. That's going to cancel the 2 and 2 here, so it's simply a third times 1 plus 1 on 32. And can anyone find a simplified version of that? What do you think we get after we simplify everything? So 1 plus 1 on 32, all of that times 1/3. What do you think we end up with at the end of the day? Sorry?
11 on 32.
Or it says 11 on 32. What do people get in chat? Let's sequence a little bit like pi. Yeah, I don't know if that's exactly. There is a formula for a sequence which relates to pi that deals with alternating signs. I don't think maybe it is exactly the one for pi.
Well, you put the formula for hyperbolic sine in one of the tutorial questions, so I wouldn't be surprised.
Yeah. Form for hyperbolic sine. Yeah, I think this might be like a, well, 11, I think it might be a multiple of pi. I can't remember off the top of my head, but there is a formula for pi which is very similar, where we alternate powers. You get something like pi on 2 or pi on 4. Yeah, that's the one I'm thinking of. If you take the odd ones, you get pi on 4. I'm not sure if you get exactly something, a multiple of pi using this formula though. Although maybe I'm just not seeing it properly. But yeah, in any case, yeah, we just want some of the first 5 values, which in this case is going to be 11 on 32 if we simplify. But yeah, there's a lot of things you can say about the entire sum. All right, so happy with using this formula? Questions, comments? I have to think about that. How about the hyperbolic? Yes, of course. Okay, so that sort of relates that question to the next part, and that is, what if we want to sum to infinity? So does it make sense to keep going a plus ar squared and continue forever? Well, let's take a look at the expression. This would be up to the nth term, some of the first n terms. And well, does it make sense to just take n to go towards infinity? Would it make sense to talk about this as a limiting sum? Well, let's think about two cases. So the first case, yeah, so what happens to Sn as n approaches infinity? If the term is too big, so if it's greater or equal to 1 or it's less than or equal to minus 1, so that's just what this absolute value is telling us. So if it's too big in magnitude, then this term is going to go towards infinity, maybe up to some sign, but it's not going to converge. We're going to either go up to infinity or minus infinity. So in this case, we can simply say that this doesn't exist. This doesn't exist as a limit. So I talked about limits. It makes sense to talk about a limit of a sequence, but we can just keep in mind it wouldn't make sense to go 1 plus 2 plus 4, right? Because these numbers would just blow up. But if our absolute value of r is less than 1, so this is between minus 1 and 1, then the numbers keep getting smaller and smaller. And it turns out that, well, this term, this decreases, right? So think back to exponential decay. This is going to decrease. This is going to tend towards 0. Which means that this expression makes sense as the sum of n terms. So in this case, we can say that the limit of the Sn terms as n approaches infinity is a on 1 minus r, because this term tends to 0. So think a little bit back to our limit ideas. And so in this case, we can say that the series converges, and we call this the limiting sum. So this has this notation S infinity. It's not really subbing in n is infinity, but it's just notation for the limiting sum. In which case, if we have that a is in the initial term and r is the common ratio, then in this case, it's important that we only apply it for series such as 1 minus a half plus a quarter, etc. Then we can talk about the limiting sum, which is a on 1 minus r. Which actually, in that case, yes, actually straight away from here, we couldn't have a multiple of pi, because it would have to be rational. So yes, but you do get odd behavior such as that, those odd sequences, because that's not a geometric series. Okay, so you can just remember this is the limiting sum as long as the absolute value of r is less than 1. As long as r is between minus 1 and plus 1, we can find the limiting sum. Let's use an example. So if you want 1 plus a half plus a quarter plus an eighth, well, how do we find the sum of this series? This is sort of a famous series. What's our a? What's our r? A is 1 and r is half, right? So, well, the common ratio is half, which is indeed less than 1, so in absolute value, so the limiting sum exists. So S infinity is a on 1 over r, and a is a half is 1, so that's 1 over 1 minus a half, which turns out to be 2, because that bottom becomes half. So there's a sort of a nice geometric meaning, and that is if you take one step, and then if you take half a step again, but then half a step of that step, then you end up taking infinitely many steps, and you end up making 2 steps overall. So there's sort of a nice idea about how that, what that means in terms of being equal to 2. What about this one? So this one's slightly different. This time we alternate signs. So it's 1 minus a half plus a quarter minus an eighth. What's the only difference here compared to the last example? Yeah, so the common ratio would now instead be minus a half, exactly. So the common ratio is minus half. This is still with less than 1, but be careful that the absolute value of minus half is plus a half. So the magnitude is still less than 1. The limiting sum exists, so S infinity in this case, the limiting sum is a on 1 minus r. It's 1 over 1 minus a half. What does this simplify as, do we think? What do we get if we take the denominator, which is now 1 plus half? 2/3, exactly, because the denominator is 3 on 2. And if we take the reciprocal, it ends up being 2/3. So it's like you take one step, then half a step back, half a step of that forward and back and forward and back, you end up taking 2/3 of a step. Okay, so that's that example. That's good so far. Okay, here's a nice interesting type problem. So for this time, we want to find the common ratio. So we want to find R. We're given that A is 10, the first term, and the limiting sum is 40. So we want to find R given A is 10 and S infinity is 40. Well, how do you think we do that? Any thoughts?
Use the limiting sum formula.
Yeah, so effectively just substitute it into that formula we're given because we've got S infinity in terms of A and R. So use the sum form. So we know that A is 10 and S infinity is 40. So solving for R, well, that's our limiting sum formula. Substitute the values in, S infinity is 40, A is 10, we're after R here. And so it's one of these type of problems where we have to solve for R. Well, I would note that it's on the bottom, so I'd probably multiply by 1 minus R, so this entire denominator, put that at the top. In fact, we can switch roles here, right? So multiply by 1 on R, divide by a 40. Maybe we should put the extra step in, so that's 40 times 1 minus R is 10. Divide by 40 would give us 1 minus R is 10 on 4, i.e. a quarter. So what do we think R is going to be equal to? We finish off to find what the ratio is.
3/4.
3/4. Do we agree with that? That's 3/4? Yeah, so it's going to be 1 minus this 10 on 4, which is 3/4. That's the common ratio. Let's try another one. Well, this is almost the same sort of problem, right? So this infinite geometric series has a first term of 8 and a limiting sum of 6. Calculate the common ratio. Same approach. A is 8, S infinity is 6. We're after R. So that's the information we're given. Solving for R. Substitute the values in, we end up with 6 is 8 on 1 minus R. Multiply by 1 minus R and divide by 6 would give us that 1 minus R is 8 on 6, which is 4 on 3. So R is going to be 1 minus 4/3, which is going to be minus 1/3. So in this case, it's actually going to be a negative ratio, which if you take a look at this, that would make sense because 6 is less than 8. So it would make sense that we would have to subtract off some values for this to be smaller than 8. Okay. Yeah, I suppose we have time for an application or two. We might save 1 or 2 for next time. Right, so this example, it's a HSC question. So we have that a tree grows from ground level to a height of 1.2 meters in a year. In each subsequent year, it grows 9/10 as much as the previous year. Find the limiting height of the tree. Well, what's the first thing we would note about about the height of this tree? I think the first thing is to give it a name, right? So let's call it Tn. Yeah, so let's say that the tree grows by Tn in the nth year. Now, what can we say about Tn? Given it grows by 9/10.
The rate is 9/10.
Yeah, it's going to be a geometric series with 9/10. One thing I should point out with these HSC questions is part of the thing that gets tested is the fact that you know it's a GP. I mean, obviously the lecture today is about GPs, but when you see this at the end of the year as a HSC student, you'd have to recognize that you'd want to use tools about GPs. So yes, it's a GP with a common ratio of 9 and 10, and the first initial value is 1.2. So it's a GP with A is 1.2 and R is 0.9, all in meters. And so if we want the limiting height, we simply want S infinity. Or, yep. So the higher the limiting height in the nth is Sn, we're after S infinity. It does indeed have a limiting sum because it only grows by 9/10. It's less, the rate is less than 1, so it will eventually stop growing. That's what it means physically. So we're after S infinity, which is A on 1r over minus r, which is 1.2 over 1 minus 0.9, and then it's just a matter of calculating this quantity, which turns out to be 12 meters, right? Because that's 0.1 at the bottom there. And just to tie it up, since it's a application type problem, we can just note the tree has a limiting height of 12 meters, just to spell that out. It's sort of just to be on the safe side. Okay, with this question. I guess just the thing with these exam type questions is just to note that it's, well, there's some application, there's some math hidden in the words, but once we understand it's a GDP and we just want a limiting sum, then it's relatively routine. And I think there's 2 more examples. Yeah, let's take a look at this one. So here's another sort of surprising application of where GDP comes in, and that is if we look at recurring decimals. So what do we want to do with this one? Well, we want to see that 0.9 repeater, so this refers to 0.99999, etc., that is actually equal to 1 exactly. So there's sort of 2 different ways you could write this in terms of a recurring decimal. That's just what that bar means, that dot means there, right? Sometimes you might see it as an overline like this. Well, how do GPs come into this? Well, let's write this as a sum. So this 0.9 repeater is 0.9999, etc. What is this explicitly? Well, it's 0.9 plus 0.09 plus 0.009. So it's 9/10ths plus 9/100ths plus 9/1000ths. And we recognize that that's a GP. I mean, what's A and R in this case?
A is 9/10, R is 1/10.
A is 9/10 and R is 1/10. Do we agree with that, everybody? Man, we're not doing trick questions. At least not here. Yeah, so A is 9/10 and R is 1/10. Yeah, and we can say that a bit easier if we note that 100 is 10 squared and 1,010 cubed, so that makes it crystal clear that we're multiplying by a 10th each time. So it's the sum of a GP with these 2 terms, and we know how to do that, especially given that it is indeed the limit sometimes it does exist. It is actually good that you check this, right? Otherwise you could write down something that doesn't make any sense. So the limiting sum would be A on 1 minus R. That's 9/10ths over 1 minus 1/10, but that denominator is simply 9/10ths. So we're dividing the first term, which is equal to the second term, the denominator, so it's just 1. So explicitly, and we note that S infinity is in fact this first term up here. So 1 is 0.9 repeater. I think I did neglect to put that last line in, but I would probably just note that there. That 0.9 repeater is 1. Great. We happy to see the last example? Or do we want to leave it for next time? Maybe I'll sort of note it here and I'll just touch base on it next time, just in case. Okay, so this is a slightly different repeating decimal. This is 0.34 repeater on both terms, so 343434. And we can still consider this as a sum of a GP. What's the first term in the common ratio? Well, let's just spell this out. How can we read 0.343434? Well, I would note that it's 0.34 from the first 2 terms, plus 0.0034 for the next third and fourth term, plus 0.0034 for the 5th and 6th terms. And so this pattern is going to continue in this form. The first term is 34 over 100, the next term is 34 over 100 squared, and the next term is 34 over 100 cubed. So we're going to get this expression, which simplifies as this. So this time it jumps by a multiple of 34 over 100. So we're repeating every 2 digits, which is where the 100 comes from. So in this case, that's our A and our R. First term 34 over 100. Sorry, R is 1 over 100. A is 34 over 100. And so to read this as a geometric series, well, what's the next thing we want to do? We want to express this as a fraction. Well, this term again is simply going to be equal to the limiting sum, given that the ratio is less than 1. So the limiting sum, well, from A and R from before, the limiting sum is exactly equal to A over 1 minus R, which is this expression. I'll note here given 1 over 100 is less than 1, just to be safe, which is 34 over 100 all over 99 to the 100 over 100. And well, that's going to be divided by the fraction is times by 100 over 99, so the hundreds cancel out. So we're left with 34, yeah, we're left with this expression, which is 34 over 99, and that's the simplest expression form, since 34 doesn't have a factor of 3 or 11. And that's it. There is also another way to get this fraction, but I might leave you to think about that, or I might touch on it next time. But this is at least how you can express these decimals as geometric series. Okay, I think that's right on time now. Any further queries or questions? One thing also I'll just quickly note here is I'm expecting that the tutorials might go a little bit slower than the lecture, so the APs won't just be today's tutorial. You might go over on Wednesdays, which will be fine. In fact, I might note to Remy right now where we're up to, at least in my tutorial. Any questions or comments so far, just generally about anything? Calculators. Give me a second. Let me just note this. The approved list hasn't been updated in some time. I'm hesitant to say anything else besides that's available, because release facelifts of the approved calculator under a different model as in given the well, put it this way, I'm expecting that you will get your approved calculators from the Nucleus Hub. So what they allow is what I'll allow. And if they're going to go strictly off the list of approved calculators, then I'm going to go strictly off the list of approved calculators. So please do do that before the exam as well, so that it doesn't take too much time for the exam. So yes, I'm going to stick religiously to the list that's given. Yes, bring in your abacuses. Get your abacus units of approved. I remember, this is not related to the thing. I know a lecturer that pulled a prank by when they had some higher ups coming into I think they were coming into a ward or something, and as a prank he got all the students to come in with abacuses just to sort of he sort of went against sort of what the course was all about. It was just it was a funny joke. I don't get any on their list anymore. Oh yes, are the abacuses UNSW approved? That's the case. Yeah, but seriously, I do want to make sure that those, because you will do the same process with exams in future. So you definitely should have your UNSW IDs, so I can check IDs, especially people that because that I haven't really seen in person, right? But so everyone should have their IDs, and you should get your calculators approved with the sticker, so that actually shows me when we get the exam underway that it's approved. It is a very standard procedure, so maybe you can tell the people at the Nucleus Hub that the list needs updating. If you feel like that's the case. Cool, cool. All right, so don't forget again, I'll say it one more time, that the REGZ submissions are due tonight, if you haven't sent them in already, and the midterm will be available Thursday, 9 AM on Moodle, and it'll be, yeah, it'll be the same sort of thing you saw last term. Most of you would have done the same thing last term. Yeah, so just be careful with the instructions and everything. Okay, any other questions before we wrap things up? All right, well, enjoy your lecture this evening if you hadn't had yours already, and I'll see you Wednesday. Thanks all, see you Wednesday. Thank you, cheers. Let me stop the recording now.